Hello, hello. 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 Hello everyone. Okay, so since no one has joined, I will just start the lecture session for today. So this is session number 5, and in the course content of this week 5, the NPTEL course by Professor Ganesh Vishwanathan had covered this order of magnitude analysis, transport coefficients, that is mass transfer and heat transfer coefficients, then relationship between momentum, thermal and concentration boundary layer, Reynolds and Chilton-Coolbrn analogies, and then we ended with a basic introduction for this forced convection. So today we will be solving numericals related to it. Before that, I will just revise few of the formulas that will be helpful to solve the questions related to it. So yes, from the order of magnitude analysis, which we did on this boundary layer theory equations, that is basically momentum balance equations, we had a few dimensionless numbers defined that will be useful to solve the numericals. So basically, by using these dimensionless numbers and the correlations, we can find the heat transfer coefficients or the mass transfer coefficients. So we will just take a brief overview of the important dimensionless numbers that are available in heat transfer or maybe mass transfers. So these are slides from Professor P. Sunt of Department of Chemical Engineering. So yes, the first number is the Reynolds number. So Reynolds number is, we define it as L rho U upon mu. That is density times the velocity of the fluid, the length of the object over which the fluid is flowing, divided by the viscosity of the fluid. So essentially, you can also call it as the ratio of inertial forces upon viscous forces. So inertia, you can write it in, you can characterize it by the velocity of the fluid, and the viscous forces you can characterize by the viscosity mu. So over here you can see that this V corresponds to the viscosity of velocity of the fluid, whereas mu corresponds to the viscosity of the fluid. That is how you can remember that this is a ratio of inertial force upon viscous force. Then depending on these values of Reynolds number, we can characterize the flow as laminar flow, turbulent flow, or whether it is in turbulent region. Then from this equation, that is Reynolds number is a ratio of inertia to viscous force, we can say that if Reynolds number is very, very less than 1, that implies the numerator is very less, that is negligible inertia, that is equivalent to a non-accelerating body, that is a body is at a constant velocity, you can say. So and that you can encounter it in Stokes flow, whereby if Reynolds number is very, very greater than 1, then we can say that the viscous forces are negligible, that is the viscosity is almost 0, that is it is an inviscid flow. So for that you can just consider it as potential flow. Similarly, we have this Peclet number that we define it as convective heat transfer upon the diffusive heat transfer. So the formula for that is LV upon alpha. So if Peclet number is less than 1, we can say that the numerator is less, that implies the convection is very less. Similarly, if Peclet number is greater than 1, we can say that the conduction is very high. Conduction is very low, that is conduction is negligible. So same Peclet number you would have encountered in mass transfer also. So in mass transfer, rather than this thermal diffusivity, we use this diffusion coefficient. So this is Peclet number for mass transfer, and this is Peclet number for heat transfer. So both are more or less similar, except this diffusivity term that is different in both of those terms. Then the other important factor is this Prandtl number. So Prandtl number is momentum diffusion upon heat diffusion. So this is the value. So this is the thermal diffusivity alpha, and this is nu, that is mu, that is the velocity of the fluid. So yes, this is basically kinematic viscosity upon thermal diffusivity. So this is kinematic viscosity, it is nothing but mu upon rho, mu upon density, and this is thermal diffusivity. So since this is kinematic viscosity, we can also remember it as that as a ratio of momentum diffusion upon heat diffusion. Then we have this Schmidt number, that is again the ratio of momentum diffusion upon species diffusion. So both the Prandtl number and Schmidt number are equivalent, but Prandtl number is of relevant when we are talking of heat transfer, whereas this same thing for mass transfer becomes Schmidt number. So you can also get an idea of the thickness of this momentum boundary layer upon the thermal boundary layer by this Prandtl number. Similarly, the momentum boundary layer upon the mass transfer, or the you can say the concentration boundary layer by this Schmidt number. That is, if we can say that if Prandtl number is less than 1, is very less than 1, that implies delta T will be higher, and this momentum heat transfer, that is this momentum boundary layer theory will be lesser. Since this thermal boundary layer thickness, that is delta T, is higher, such cases can be encountered in liquid metal. That is, there is a conductivity, but the velocity of the fluid or the boundary layer of the momentum is low. Whereas in case of heavy lubricant oil, you can say that Prandtl number is greater than 1, very greater than 1. Same thing you can conclude for Schmidt number. Then we have this Nusselt's number. So Nusselt's number is the ratio of HL upon K, but it is not, you cannot define it as a ratio of convection to conduction. It is basically a parameter to judge the temperature gradient. So this will be equivalent to the temperature gradient across any geometry. So this Nusselt's number is a dependent variable, not an independent variable. That is, it will be dependent on the geometry of any object. So basically, these parameters alpha, beta, C will be dependent on the geometry or other parameters. Similarly, for mass transfer, the same Nusselt's number becomes the Sherwood number. Again, it is not a ratio of convection to conduction, but you can characterize it by the concentration gradient. Then this is the Bayer number. We already covered this in this lumped capacitance or the transient analysis that we were studying. So it is the ratio of resistances in series in two different medias. That is, if you are having a solid object that has been dipped in a fluid of some constant temperature, then for that system you can define this Biot number as the solid conductive resistance upon convective resistance. Then other dimensionless number that you can get from the order of magnitude analysis is this Fourier number. Again, this is not a parameter, it is not a dependent variable, so basically it is a dimensionless independent variable. So this Fourier number also we covered when we were discussing this transient analysis. Then the last number is Grasshoff's number. It is related to you will study it in forced initial convection. Okay, so I don't think there is anything else. Then there are these few analogies between mass and heat transfer. That is how both the transfer processes are similar, or how you can use the correlations. So one thing to keep in mind is the Nusselt's number that is used to calculate the transfer coefficient, either the heat transfer coefficient or mass transfer coefficients, will be a function of eta. So this is the parameter of a geometry, that is x by L, then Reynolds number and Prandtl number. That is, for a given for a given geometry, if we have been given Reynolds number and Prandtl number, then using any correlation we can calculate this Nusselt's number. It won't depend on any other parameters except these three parameters. Similarly, for Sherwood numbers, in terms of mass transfer, you can write the same, but in terms of mass transfer, the equivalent of Prandtl number becomes Schmidt number. Then this is a correlation between the heat transfer coefficient as well as this mass transfer coefficient. That is, H is the heat transfer coefficient and HM is the mass transfer coefficient, and their ratio you can find it by these equations. That is the thermal conductivity upon diffusivity, then the length, then e raised to -1 upon n. So n is a parameter that will be mostly provided to you in the question. Then basically by using this equation, if you have either of the heat transfer coefficient, you can find the another one. So this is an important correlation that you might need to remember. And this LE is nothing but Lewis number. I think I incorrectly said it as length. So this LE is Lewis number as defined over here. So these correlations were obtained by the analogy of heat transfer with mass transfer. Similarly, if we derive an analogy between momentum with heat and mass transfer, we can get this friction factor, that is CF, that is the ratio of stress upon the inertial term, that is half of rho velocity square. So this formula will be again useful to you. Then there is this formula related to Reynolds-Chilton Coulomb analogies, so that we will see when we solve the questions. Then at last there was this force convections. So there are much numericals related to force convection in this class, so I will discuss this topic in the next class. Meanwhile, if you have any doubt, you can just ask me. So yes, before starting with the numericals for today's question, if you have any doubt, you can just ask me, or else we can start solving the question. So let's start with solving the questions for today's lecture. So this is question number 1. So the question states that a dry air at 32 degrees Celsius flows over a wetted plate of 0.2 meter square per area. So let's consider the plate as a square one. And the area is given as 0.2 meter square. The dry air flows at 32 degrees Celsius. That is, again, it has been given that the plate is wetted. So let's just consider that this is a wetted. So these are all the water molecules shown by the green line. Then we have been given that air is flowing at a temperature of 32 degrees Celsius. Okay. So over here, air is flowing at temperature of 32 degrees Celsius. The average convection coefficient is given as 20 watt per meter square Kelvin. The heated power required to maintain the plate at a temperature of 27 degrees Celsius is 432 watt. This power is 432 watt. And the temperature of this plate is 27 degrees Celsius, whereas the ambient air temperature was 32 degrees Celsius. Then we have been given this data and we have been asked to find the mass transfer coefficient. So you can see that there is this temperature difference. So the air is flowing at 32 degrees Celsius, whereas this wet plate is at a temperature of 27 degrees Celsius. So due to this temperature difference, there will be heat transfer occurring between both of these objects. Correct? So that this heat power will add to this heat heat transfer. Correct? Because over here we are providing some power, so this power will ultimately get dissipated due to this heat transfer also. Similarly, this air would be having okay, so we have been given dry air, so this air won't be having any moisture or water content, whereby this plate is having some water content. Correct? So due to this concentration difference of water content between air as well as plate, the mass transfer will also occur place, and again that will be facilitated by this power that has been provided. So basically, if you just write an energy balance, what you can see is the power will be responsible for this evaporation as well as convection. So what we need to do is we need to equate this power to the mass transfer rate, and convection is basically heat transfer rate. So if we just write that, we can get, I think we will try to find this mass transfer coefficient from that. And then in the second question, we have been asked to find the power if the wetted plate is maintained at a temperature of 37 degrees Celsius in dry air of 32 degrees Celsius. So earlier, if the wet plate was at a temperature of 27 degrees Celsius, the power was 432 watt. Now they asked that if the temperature of the plate is 37 degrees Celsius, then what would be the power required if the convection coefficient remains unchanged. So yes, let's try solving this question. So I have shared the questions with you. So as discussed, the power will be equal to the power due to, let's say, evaporation plus let's say heat transfer. So this will become NA plus QA is equal to power. So this mass transfer, you can write it as the average mass transfer coefficient that we have to find. Then this evaporation, due to this evaporation we need to add this enthalpy, that is HFG, and there will be this concentration difference, that is rho AS at the surface of the plate as well as rho A infinity, that is in the dry air. Then we have this heat transfer. Basically here we will be also having area. Similarly, the convective heat transfer will be HA delta T, that is the heat transfer coefficient H bar. This is mass transfer coefficient HM, area, and the temperature difference, that is temperature of surface minus temperature of the dry air. And power we have been given as 432 watt. So you can replace the values in this equation and try to find HM. So if you just replace all those values, we can get it as 432 is equal to, let's keep the area as common, H bar M is unknown, HFG is given as this 2.438 into 10 raised to 6 into, at the surface the concentration is given as this 0.02556 0.02556 minus of 0 plus the heat transfer coefficient is given as 20. Temperature of surface was maintained at 27 degrees Celsius and the dry air was flowing at 32 degrees Celsius. And the area is given as 0.2 meters square. So yes, you can try solving this and you can get the value of H bar M as 0.033. Now in the second question, what we have been given is the wetted plate is maintained at a temperature of 37 degrees Celsius. So here this Ts will become 37 degrees Celsius. The convection coefficient, that is H bar M and H bar, remains the same. And also since the temperature of the wetted plate is changing, the concentration will change, that has been given, as well as this enthalpy of evaporation at 32 degrees Celsius will change, and that has also been given. So you can again put those values over here and try to calculate the power by using this equation. So the power will come around 784 watt. You can try solving it on your own. If you have any doubt, you can ask me, or else we can move on to the next question. Just go through the question, just go through the solution that I am sharing, and if you have any doubt, you can ask me. So this is the solution. So let's move on to the next question. This is question number 2. So the question is, a 20 mm diameter sphere is suspended in a dry airstream with a temperature of 22 degrees Celsius. The power supplied to an embedded electrical heater within the sphere is 2.51 watt when the surface temperature is 32 degrees Celsius. So that is, we have been given a sphere, and within this sphere we have embedded an electrical heater. So you can just call it that we have an electrical heater over here which has a power of 2.51 watt. For this system, we have been asked to find the mass transfer coefficient as well as the power required to maintain the temperature 32 degrees Celsius. We have been given a hint, that is we have to use the heat mass analogy with n equal to 1 by 3. So this is the equation that we already saw. So you can use this equation to find the correlation between the heat transfer coefficient as well as the mass transfer coefficient. So what you can try doing is you can just write an energy balance over here. So from that energy balance you can find this heat transfer coefficient H. From that you can find this HM. So the first case, we haven't been given that this sphere has any water. Okay, so since the sphere doesn't have any water, there won't be any mass transfer. So you can just neglect all the mass transfer terms in this heat equations. Whereas in second case, we have been given that the surface has a thin porous covering saturated with water. So for second case, you need to consider the mass transfer also. Just keeping all these things in mind, try solving this question. We can discuss it after 10 minutes. So okay, let's try to see the solution of this question. This question is very similar to the previous question that we discussed. However, there is only one catch, that in this question, for the first case, we don't need to consider the mass transfer because the sphere doesn't have any fluid that can evaporate or whereby the mass transfer can take place. So yes, we were given a sphere which has an heater of power 2.51 watt, and there is no fluid in this or over this sphere. Then we had to find the mass transfer coefficient by using the heat mass analogy. So basically all the power will be dissipated by the heat transfer, not via mass transfer. So if you just write the energy balance, so basically all the power will be this due to the Q of convection. So you can just equate the power given as 2.51 watt to HA delta T, that is Ts minus T infinity. The heat transfer coefficient has been, so heat transfer coefficient we can find over here, and there won't be any term related to this mass transfer. So this H will become 2.51 upon the area. You can write it as pi d square, that is 20 mm. So it will become 0.02 meter whole square upon the temperature difference, that is at the surface we have the temperature of 32 degrees Celsius where the ambient air temperature is 22. So delta T will become 10. So from this you can get the heat transfer coefficient as somewhat around 200 watt per meter square Kelvin. Now in the question we have been asked to find the mass transfer coefficient, and then we have been given this correlation that we can use. So from this correlation we can write that H upon Hm, that is what we have to find the mass transfer coefficient, will be equal to rho Cp Lewis number raised to 1 by n. This rho Cp Lewis number raised to 1 by n. The value of n is 1 by 3, so it will become 1 minus 1 by 3, that is 2 by 3. So from this the mass transfer coefficient will become H upon rho Cp L raised to 2 by 3. So what else we have been given in this question? We haven't been given the Lewis number, but we can write it as alpha upon diffusivity, that is thermal diffusivity upon the mass transfer diffusivity, alpha upon D raised to 2 by 3. Now you can put all those values that we are having in this. So the value of heat transfer coefficient we found out as 200 upon density is given as 1.1614 and Cp is 1007. Alpha and D are 22.5 into 10 raised to minus 6 upon 0.26 into 10 raised to minus 4 raised to 2 by 3. So as you can try simplifying this, you can try to calculate it, and the value of the mass transfer coefficient, that is H bar m, you will be getting it as 0.188 meter per second. So this is the mass transfer coefficient, that is if there was some water present on the surface, then the overall water evaporated, you could have calculated by using this mass transfer coefficient. Now in the second case, we have been given that how much power is required to maintain the sphere at 32 degrees Celsius if the outer surface has a thin porous covering saturated with water. That is, we have been given that power, we have to find that it will be equal to again this mass transfer rate plus the heat transfer rate. So the heat mass transfer rate we saw in the previous question as h bar m into hfg upon rho at the concentration at surface upon the concentration at infinity, which is ambient air, upon h bar ts minus t infinity, and the whole was multiplied by the area. So yes, you can try replacing the values over here, and ultimately the power that you will be getting is 21.8 watt. So again, take a look at the solution for a couple of minutes, and if you have any doubt, you can ask me. We can look into it. If you have any doubt, you can ask me. So try solving this third question. We will discuss it in a while. So in this question, you have to use this specific correlation, that is Nusselt number correlation with Reynolds number and Prandtl number. So this is a new thing that we will be solving in this question. So let's take a look on this question number 3. So we have been given that the defroster of an automobile functions by discharging warm air on the inner surface of windshield to prevent condensation of water vapor on surface. The temperature of air and the surface convection coefficient must be large enough to maintain a surface temperature Tsi that is at least as high as the dew point. Consider a windshield of length L equal to 800 mm and thickness T is equal to 6 mm and driving conditions for which the vehicle moves at a velocity of v equal to 70 miles per hour in ambient air at T infinity of minus 50 degrees Celsius outside. Then from the laboratory experiments performed on the model of vehicle, the average convection coefficient on the outer surface of the windshield is known to be correlated by an expression of the form Nusselt's number is equal to 0.03, Reynolds number raised to 0.8, Prandtl number raised to 1/3. Where Reynolds number, we have been given the formula of Reynolds number, and then we have been given this air properties. And the question we have been asked is, if the dew point is 10 degrees Celsius and the inner car's inner temperature is 50 degrees Celsius, what is the smallest value of HI, that is the heat transfer coefficient, required to prevent condensation on the inner surface? Then we have been given some parameters. So yes, we have been asked to find this heat transfer coefficient HI. So if you just draw a resistance diagram for this entire system, you will be getting a more clearer idea so as to how to find this HI. So let's just consider this as the front glass of the automobile. Okay, the thickness of this glass we have been given as 6 mm and the length is 800 mm. So length is 800 mm, thickness T is 6 mm. The velocity of the car is 70 miles per hour, so this will come around 31.3 meter per second. Then we have been given that this ambient air temperature T infinity is minus 15 degrees Celsius. Okay, so outside we are having minus 50 degrees Celsius. At surface, let's just call the temperature TS0. On the inner side of the glass, the temperature is TSI, and inside the car, the temperature is T infinity I. Then we have been given this Nusselt's number correlations. The dew point is 10 degrees Celsius. So basically, this should be equal to what have been the, we have been given that the surface temperature TSI should at least be dew point. That is, you can just equate it to the dew point, that is equal to 10 degrees Celsius, and the inner temperature is 50 degrees Celsius. And then we have been asked to find the heat transfer coefficient HI over here. HI. Have we been given H0? So H0 we haven't been given, but we have been given this Nusselt's number correlations. So basically, the average convection coefficient on the outer surface is correlated by this equation. So H0 we have. So since there are these composite modes of conduction occurring, so over here we will have convection, conduction and convection. We can draw a resistance diagram to get an idea of what all things we are having. So let's consider this as the extreme outermost point. It's the temperature of T infinity 0. Then there will be this convective resistance until we reach the glass. So the surface of the glass is TS0. Then there will be this conduction within the glass, and on the inner side the temperature is TSI. Then there will be this convection inside the car, and the temperature is T infinity I. So we have this temperature, and this as dew point. Then this outer convection H0. So the resistance for this will be 1 upon H0. Over here it will be thickness upon K, that is delta X upon K. Similarly, over here will be 1 upon HI, and we have to find this HI. But for that, first we need to find this H0 and then use this resistance concept. H0 we can get it from Nusselt's number correlations. So Nusselt's number we can write as Nusselt's number is equal to 0.03, Reynolds number raised to 0.8, Prandtl number raised to 1/3. So first let's just calculate the Reynolds number. So Reynolds number is velocity, so V upon kinematic viscosity mu. The velocity is given as 70 miles per hour, that is basically 31.3 meter per second. The length of the windshield is 800 mm. The viscosity nu we have been given as this. So yes, 12.5 into 10 raised to minus 6. From that we can calculate the Reynolds number as 31.3 into 800 into 256 divided by 12.5. So it roughly comes around, so this is mm, so there will be 10 raised to minus 3 term over here. So the value is, this will get cancelled out. So basically it comes around 2 into 10 raised to 6 approximately. Then we need to find this Nusselt's number. So Nusselt's number is nothing but HL by K, H naught L upon K. So from this we can get H naught. We just need to replace the values in the correlation. 2 into 10 raised to 6 raised to 0.8 into Prandtl's number is given as 0.71 into 1 by 3. The length is already given as 800 mm. And the thermal conductivity K is given as 0.023 watt per meter Kelvin. So H naught will become 0.03 upon 0.8 into K is, I think, 0.023 into 2 into 10 raised to 6 raised to 0.8 into 0.71 raised to 1 by 3. So you can try solving this and you will be getting the value of H naught as around 84.6 watt per meter square Kelvin. So once we have this H naught, now we need to use this resistance diagram in order to find Hi. So from this diagram, we can write, so we don't have this term, but we are having this Tsi and T infinity as well as this. So what we can write is, we can just consider this as one composite block and equate the heat transfer from this block into this block, and that will become T infinity I minus of Tsi, we are going in this direction, upon 1 upon Hi is equal to, since we are in this direction, Tsi minus of T infinity naught upon 1 plus H naught plus T upon Kg. So now we can replace all those values over here and you can try to find the value of Hi. So Hi will go over here, so it will become Tsi minus of T infinity 0 upon T infinity I minus of Tsi into 1 upon H naught plus thickness upon K of glass. So Tsi, that is surface temperature, is the dew point, that is 10. Then the outside temperature was, I think, minus 15 degrees Celsius, so minus will become plus 15. Inner temperature is 50 degrees Celsius, minus surface is 10. 1 upon H naught we calculated it as 84.6 plus thickness is 6 mm, 6 into 10 raised to minus 3, and K is I think 0.023. K is 0.023. So yes, you can try simplifying this, and the value of the heat transfer coefficient on the inner side will be around 38.8 watt per meter square Kelvin. So yes, you can try doing this. So this is the solution. And now let's move on to the another questions. This is a relatively simple question, whereby we have been given consider conditions for which a fluid with a free stream velocity of v equal to 1 meter per second flows over an evaporating or subliming surface with a characteristic length of 1 meter, providing an average mass transfer coefficient of 10 raised to minus 2 meter per second. Calculate the dimensionless parameters: Sherwood number, Reynolds number, Smith number, and Jacobs number for airflow over naphthalene. So yes, given these conditions, we have been asked to find this Sherwood number, Reynolds number, Smith number, and Jacob number for mass transfer, that is Jm. So you can try solving this. It's a fairly straightforward questions, but I will just share the formula. So Sherwood number is nothing but the Nusselt's number for mass transfer, so it will become HL upon diffusivity DAB. Reynolds number is same, that is rho Vd upon mu, or you can also write it as velocity L upon nu viscosity, kinematic viscosity. Smith number is mu upon DAB, that is equivalent of Prandtl number, and this Jacob number you can get it as Stanton number into Smith number upon 2 by 3, or you can, this STM is HM upon velocity into Smith number raised to 2 by 3. So using this formula, try calculating the value of all these dimensionless number, and then I will share the solution with you. So these are the final values of the dimensionless number. You can just see it and verify your answers. So let's move on to the next question. So similar question we have already discussed in last class, so I will just skip it. So this is question number 6th. So again, this is very similar to the questions that we discussed today. So let's take a look on this question number 7, because here we need to use a Chilton-Coolber analogy. So that will be a new thing for you. So try to read the question and solving it on your own, and then I can try to solve it with you. So let's see the solution for this question. So yes, in this question we have been given that the experimental results for heat transfer over flat plate with extremely rough surface were found by these equations. Okay, so we have been given a flat plate with extremely rough surface, and for this the Nusselt's number correlation is given by these equation. So this is a local Nusselt's number, that is NUX 0.04, Reynolds number x raised to 0.9, Reynolds number raised to 1/3. Okay, then airflow, we are having an airflow at 50 meter per second, so that is velocity. V velocity is 50 meter per second, and we have been asked to find the surface stress, that is tau s, from the leading tau s at x equal to 1. So this we have been asked to find. So we know that this factor Cf we defined as friction coefficient defined as tau s upon half of rho u infinity, that is velocity square tau s, and here we have been asked to find tau s, that is tau s is equal to Cf into half of rho velocity square. For that we need to find this Cf. Cf we can find by using this formula given over here, that is nothing but Chilton-Coolbrith energy given by these equations. Then we replace the value of Stanton number and Prandtl's number, then we again replace the Nusselt's number correlation of this, and we get this final formula. In this formula you can replace all those values of Reynolds number, Prandtl number, and you can get the value of Cf. So in order to do that, first let's calculate the Reynolds number. So Reynolds number is rho Vd upon mu, or you can just write velocity x upon kinematic viscosity mu. So this you can replace the values as velocity is 50 meter per second. The length is I think 1 meter that we have been given. The kinematic viscosity is 15.89 into 10 raised to -6. So the Reynolds number will come around 3.15 into 10 raised to 6. Prandtl number we have been given as 0.71. So from this you can calculate the Nusselt's number, put it over here, then again replace the Reynolds number and Prandtl number over here, and ultimately you can calculate the value of Cf as 0.0179. This will be the value of Cf. So in order to find this stress tau s, you can just multiply the Cf by half of rho velocity square that we saw over here. Then we need to replace all those values, so it will become 0.0179 by 2. Density is 1.16. Velocity is 50 meter pulse. Velocity is 50. So you can try solving this, and the value of tau s will be Here we are having square. So it will come on 25.95. 25.95. Since this is stress, its unit will be Newton per meter square. So tau s we calculated it as 25.95 Newton per meter square. So yes, that was all related to the today's class. So yes, if you have any doubt related to the questions discussed or the course content of this week, you can ask me. I will be here until I think around 10-15 minutes. I will be here, or else you can end today's session. I'm just sharing this another question that you can try solving it. I will just straight away share the solution with you. Meanwhile, if you have any doubt, you can just ask me. So the solution to this question, if you want to solve, you can just see it over here. Okay, so let's end today's session. I don't think anyone is available.